The method of undetermined coefficients. I'm going to give you an overview of the topic and then do two examples. If you need any help getting up to speed on the basics of differential equations, I've got a playlist on that. Here we have a set of differential equations together with their corresponding solutions. As you can see, the left sides of all the equations are the same, and the first two terms of the solutions are all the same. The terms on the right side of the equation are all different, and these extra terms over here are also all different. This follows from this, and this follows from this. The method of undetermined coefficients is how we get from here to here. Now notice that the first equation here is homogeneous. The solution to this homogeneous equation carries through in all of these other solutions. The standard way to solve non-homogeneous equations like this involves two steps. The first step is to actually find the solution to this homogeneous equation first. And in that context, we would call this the associated homogeneous equation. And this solution would be the complementary solution, YC. Now, there are various ways to solve this homogeneous equation, but I'm going to skip all that. Have a look at my playlist if you need any ideas for how to do that. The second step is to use the method of undetermined coefficients to find these other parts of the solution. We call that the particular solution, YP. And you have to find the complementary solution first because the complementary solution can influence how the particular solution turns out. And we will see that happen in my second example. Now notice something else. The complementary solution has arbitrary constant coefficients. You can put any constant value in here you like. Could be a negative, radical, could be 0, could be pi, whatever you want. And anything that looks like this will be a solution to this homogeneous equation, which means that if you take the first derivative and the second derivative and substitute for y prime and double prime and add everything up, everything will cancel out and you will get a 0. Over here, on the other hand, we have coefficients that are not arbitrary. So not just any coefficients will do. If you take the derivatives of this and substitute into here and simplify, you will get 4x squared, but you're only going to get that 4x squared if you have a 2 and a negative 6 and a negative 7. Any other coefficients will not work. Now, of course, when you first start the problem, you don't know what the solution looks like yet, so you certainly don't know what these coefficients are. So at first, they are undetermined, and then you use this process to determine them. And there they are, they've all been determined. So let's try solving this equation. The left-hand side is the same as what we just saw, so we already know what the complementary solution is going to be. How do we find the particular solution? Well, it's almost guess and check. When you look at these terms here, you see an x squared and an x. So presumably, there must be at least one x squared over here somewhere, and there must be at least an x term over here. So we expect our particular solution to have an x squared term, but we don't know what the coefficient is yet. So I'll just call it ax squared. But maybe we need an x term as well. So I'll try bx. Now, if you take the derivatives of these, you'll get this. Now, notice we have some constant terms there. But there are no constant terms over here, which means if you've got a constant here and here, they're going to have to cancel out. But the truth is, there might even be a constant term in here. Maybe you have constants in all three of these terms that are going to cancel out. So we really need to be careful and put one more term over there. Now, why not an x cubed term? The derivative of x cubed has an x squared term, so we could have an x squared there, which would be a match, and so on. But the problem with that is that if y has an x cubed, all of the derivatives are going to be lower powers, and there's no way you're going to cancel out the x cubes, which you would need to since there's no x cubed over here. So let's substitute this stuff in and see what happens. And we just got to do some basic algebra. I'll distribute all of the constants so we don't have any more parentheses. I suggest we gather together like terms. There's only one term here that has an x squared, so I'll put this over here. We've got a couple of terms with x, 6a, 2b. I'll factor out the x. And then we have, looks like 3 more terms, 2a, 3b, 2c. Now the next step, I'm going to subtract these terms and then group them with this stuff over here. People usually skip this step, and you'll see why. So there's negative 2x squared. And then we'll subtract 6x, and then the other term stays the same. At first, it looks like we're in big trouble because we have one equation with 4 unknowns. Ordinarily, you need 4 equations to solve for 4 unknowns. But we don't need to do that because x is special. X is a variable. X can be any value you want from negative infinity to positive infinity, and this equation is supposed to be valid for any possible x value you can think of. The only way to make sure that that's true is to set all of these individual terms equal to 0. Now there's a technical reason why this is the only way to solve this, and it has to do with the fact that these 3 terms are linearly independent, but don't worry about that if you don't want to. So we can see if this is equal to 0, we get... Now what people usually do is they just skip straight from here to here. They just match up the terms, that, and then of course there's nothing there, so it would be a 0. And now you solve for this. If a equals 1, we have 6 plus 2b equals 6, so 2b equals 0. And now you've got a 1 there and a 0 there, so 2 plus 2c equals 0. Now I made this part easy on purpose, but of course when you're doing a problem, you may have to spend a lot of time on this part using your high school algebra skills to sort out the solutions to all these linear equations. Regardless, we've got a solution for a, b, and c. We put them in there. There's our particular solution, and there's the general solution. Now remember this when we do the next example. All right, here's another example with the same complementary solution as before. Now we need a solution that includes e to the power of negative x. Now there's a problem with this solution. It's not the right solution. Let's see what happens when we substitute. A minus 3a plus 2a is equal to 0. So we've got 0, e to the minus x equals 3, e to the minus x, 0 equals 3, which is obviously no good. What is this telling us? Well, it's not telling us that a equals 0. There's no a here, there's no a there. The a's all canceled out. What this is telling us is that because 0 equals 3 is impossible, so is this solution. The problem is that this right here was part of our complementary solution. And we already knew that when you take the derivatives and substitute, you get a 0. You can't possibly get anything other than 0 over here. So if this doesn't work, what can we do? Here's what we can do. Multiply by x. Watch what happens when I take the derivatives now. So now let's substitute. So a minus 3a plus 2a is 0. Negative 2a plus 3a is a. And when we match up the left and right sides, everything is fine. We have a 0 on the x e to the negative x term here, which makes sense because there is no x e to the negative x term over there. And then we have an a matching this 3. So there's our particular solution, and there's our general solution. So here's how you should pick your trial solution. Whatever non-homogeneous term you have has to have a matching term over here, And there also need to be terms corresponding to any possible derivatives of this term that matches this over here. So there's how power functions work. If you have a sine, you also need a cosine. Derivative of an exponential is an exponential. It's simple enough. If you have more than one term, then both terms need to be accounted for. If your term is in the form of a product, then you need to consider all the possible derivatives that you would get using the product rule. Now, all of this assumes that none of these terms match any of the terms in your complementary solution. Any terms that do match need to be multiplied by x, which means you might get an x squared there, or an x cubed there, or what have you. Thank you very much for watching. Please like and subscribe. And there's a link there to my differential equations playlist.